Sure. So get started.
Can we start?
Yeah, sounds good.
All right. Hi, everyone. Let's get started. It's my pleasure to introduce my advisor, Professor Peter Abil. For those of you who don't know him, he's a professor at UC Berkeley, and he's basically worked on a lot of the fundamental things that we use in DeepRL today. So he's going to talk about deep learning to learn for robotic control today.
Okay, thanks, Abhishek. Can everybody hear me well? Does it work for the recording in the back? Yeah? Thank you. Okay, good morning. Not working. Let's see. I guess I'll be parked over here. Okay, so what I'd like to tell you about is reinforcement learning, which the class is all about, and then specifically how we might learn reinforcement learning algorithms rather than design them by hand. So let's start with the problem setting. In reinforcement learning, the goal is to learn a policy, let's say policy pi theta, that can decide what to do in a current state. So it might emit a distribution over actions given current state. Then when the action gets taken, robot and environment change state, and this process repeats over and over. And at any given time, associated with the state that the environment is currently in, there will be a reward. Often it might be 0, and maybe then 1 when you achieve a goal, or it could also be negative for bad events and so forth. And the goal is to optimize expected reward. This has many applications, not just in robotics, also in marketing, advertising, dialogue, power management, and so forth. Anytime we have a problem where a decision you make right now affects the state of the world, and we need to deal with the consequence of the actions. Challenges people have encountered compared to supervised learning are that once you have a feedback loop, you can have stability problems. Let's say you have a okayish policy, and you make an okay decision, then at the next time you'll be in a not so great situation where your policy might have even more trouble making the right decision and things will destabilize. Another big challenge is credit assignment. Credit assignment is the issue of understanding when something good or bad happens, what it is that you did in the past that was fundamentally contributing to the current event. And then exploration. To do something better than what you've done before, you need to try new things. And so these are classically the three big challenges people try to address when designing by hand, typically reinforcement learning algorithms, and try to improve the algorithms with some of these ideas in mind and in making progress on one or more of these axes. And actually, people have been pretty good at it. Especially recently, there's been quite a few breakthroughs. For example, learning to play Atari games, all the way from raw pixels to actions. Many papers on that, and very good results. Better than human-level performance on many of the games, not all of them, but many. Then the game of Go, AlphaGo learned from first imitating human play and then reinforcement learning on top of that. AlphaGo 0 learned with pure reinforcement learning, self-play, no imitation involved at all. Another example is reinforcement learning for learning robotic control. This is some work that was led by John Schulman, who was a PhD student here until recently and then helped found OpenAI. So what you see here is the reinforcement learning in action. Probably Sergey or someone else has shown this video earlier in this class. What's really intriguing here is that you can, as a roboticist, you can abstract away what robot you're working with. It doesn't matter whether it's a two-legged robot or it might be a four-legged robot or yet another type of robot. One same algorithm is able to optimize control for a wide range of systems. And so as opposed to, let's say, 10 years ago, if you were to visit a robot locomotion lab, then you might have visited a two-legged locomotion lab or a four-legged locomotion lab, and people would have talked about zero moment points and thinking about center of gravity, and should there be 3 feet on the ground, or is it dynamic locomotion versus statically stable locomotion? All those things we're just throwing out now, and we're just having the system learn on its own what it's supposed to do to maximize reward. The reward here is very simple. The further this way, the better. And the less impact with the ground, the better, and the lower torques applied, the better. So it's just 3 components, nothing in there about what walking looks like, yet it can invent walking, or in this case, the reward is how close the head is to standing head height. The closer, the better, and it can invent this on its own. Almost. There we go. Here's another one on a real robot. This is actually some of the work Sergey did when he was a postdoc at Berkeley, together with Chelsea, and then Trevor and me. What you see here is the robot learning to place this block onto the corner spot. And this actually works in about 10-20 minutes of real-time attempts of placing that block. It figures out a policy to place it reliably in that corner spot. In fact, that success at the time had Sergey and me connect with NASA on seeing if we could have a reinforcement learning algorithm learn to control their robot. This is a Super Bowl robot. What does this robot do? It's supposed to do planetary exploration. Why is it designed this way? It's cables and rods. What you can do is you can actually pull the cables, shortening the length of those edges. And by doing that, the center of gravity will shift, and this will roll over. And that way, it's like one big wheel, omnidirectional wheel, a sphere that you can steer around and may go in any direction, or at least that's the intent. But they actually had a lot of trouble designing reliable controllers for this. And so we started collaborating with them on having reinforcement learning learn the policy that can control this robot. Another reason you want a robot like this, at least they design it this way, is that it's very compressible. So if you put something in a rocket, volume matters a lot. And so you can compress this down to almost planar and send many of those in a small volume to, let's say, Mars. For this one, we actually ended up training fully in simulation, but in many different versions of the simulator to make it a robust policy that then ended up also working on the real robot, because learning on the real robot was actually a little tricky to set up and would have been very slow. But ultimately, the policy did work on the real robot. Now, everything I've showed you so far is really solving the mastery problem. That is, there is a task to be solved, let's say rolling the Super Bowl or getting a robot to go forward, and then a policy is trained to become really good at doing that. And with really good, we see, for example, for Atari, could be better than human level performance on the game of Pong here. But mastery on one task is maybe not exactly what we ultimately want. Maybe what we want is also to look at how long it takes to learn something and see if we can start learning much more quickly. Because if we can make the learning happen quickly, then we could deploy that system, the learning system, into a new environment that it has not seen before and acquire new skills in that environment rather than first training and then deploying. And so for Atari, DQN took 40 days of real-time play, whereas humans take about 2 hours to saturate their levels in this kind of game. And so clearly one is slower than the other, and the question is, can we get closer to the fast learning somehow by designing maybe better algorithms, or how do we get there? The slide I'm showing here, I borrowed from Andrej Karpathy, and it kind of conveys pretty well a lot of my current thinking about this, which is that as we look at trying to improve algorithms, the amount of compute we have plays a big role in what actually we do and works the best in the real world. This one is for computer vision. And so what we see on the horizontal axis here is different approaches to trying to solve computer vision, some anticipated future approaches. And then on the vertical axis, the type of data being worked with. And so what this is showing is kind of a big picture historical overview, is that initially when people were doing computer vision, they just looked at one image, the Lena image, and that was it. And if your algorithm did the right thing on that one image, that was a success, that was a great algorithm. That was fine at the time, and people build up some understanding of computer vision that way. But then when you want to do something more complicated, like analyzing what's in an image from the Caltech 101 data set, hard coding something wouldn't work anymore. So people start using machine learning. What kind of machine learning? Well, they designed image features. They essentially designed all kinds of versions of histogram of edges representations of images. Why was that the best solution at the time? Well, with only 100 images, or a small number of images, 10 to the 4, so about 10,000 images, there's only so much you get from that data. So as a human, you still need to infuse a lot of information into your vision system if you only have that much data to try to maximize performance. And so combining human ingenuity with a small amount of data, that's what you had at the time, was the best way to achieve top performance at that time. But then as data sets became bigger and bigger, the trend went from a lot of human involvement to less and less and less human involvement. For confidence, humans might still specify an architecture, but not the details of what each layer should be doing, and just let the data speak for itself. And so confidence are the ones achieving best performance now, and it's likely that confident architecture searches, and then beyond that, other more automated approaches, as we get more and more data, will start getting even better performance in the future. This yellow line here is an interesting line to look at. The zone here, Andre called zone of not going to happen. What he meant with that is if you're going to hard code things, you're not going to get things to work for anything that involves many, many images, even just 10,000 images. It's just not practical to hard code all the ideas to get good performance on something like this. And so as we get more compute, more data, we can actually move up and closer to solving everything computer vision, hopefully in the foreseeable future. We can think about something similar for reinforcement learning, actually. If anything, reinforcement learning might benefit even more from having more compute, let the data more speak for itself, because reinforcement learning has many more challenges than computer vision. Computer vision is a pattern recognition problem. There's an input and you need a corresponding output. There is no stability issues. There is no credit assignment issues. There is no exploration issues. So there's a lot more challenges in reinforcement learning, making it a lot harder to make progress on it ourselves. And so a corresponding graph also borrowed from Andre is here for reinforcement learning, where we say if we hard code things, let's say we write some Lisp program that moves blocks around in Shardlu, that was fine in the 70s. As we got further along, got more compute, we could run something like value iteration that could solve small MDPs, let's say grid worlds, and get good performance on that. But then as we want to solve bigger and bigger problems, we need approaches that involve more and more learning. DQN, policy gradient methods allow to solve Atari games, some Majoko environments. What if we want to go beyond that, like any kind of video game, any kind of digital world? It seems like we might be hitting the limits of our hand-designed algorithms, and maybe if we let the computer design the algorithms for us, we can actually make a lot more progress. In reinforcement learning, we're not so much data constrained the same way supervised learning is. In reinforcement learning, it's all compute, because you generate your own data. So as we get more and more compute, we can move more and more to the right on that axis, and it's likely that people who work somewhere here will have whatever code they run lead to emergence of new reinforcement learning algorithms that are better than what anybody can hand design. So this is the zone I'm personally most excited about right now, how to get far to the right there and get things automatically generated. Yes?
I think if you look at nature, right,
Mm-hmm.
humans have hard-coded structures. My brain is hard-coded. And the part I get to learn is only beyond like what ways to put in my head.
Mm-hmm.
So, and actually like the biological design, if you believe in evolution, is chosen by nature, which is like sort of like an evolution algorithm. But
Mm-hmm.
it's somewhat hard-coded. So why do you think that this is also the part that should be learned by gradients?
Why it should be learned by gradients?
Right, like the actual structure and in the code.
I'm not saying it has to be learned by gradients. You can learn it with different optimization methods. If it's a discrete thing you're optimizing over, gradients wouldn't work maybe. But I would say it's actually the same thing. If you look at evolution, evolution is actually operating somewhere here, had an enormous amount of compute power, had billions of years of working through things. And that's a lot more than anything we've been able to use so far. But in my mind, evolution lives somewhere on this end of the spectrum, having gone through that whole process over the past many billion years. Yes?
So you mentioned compute a couple of times and more compute. Where do you think in time are we going to hit basically a computational bottleneck? Because surely, I don't know, Microsoft and Google might be able to have like supercomputing, clusters and stuff like this to perform this, but I don't have it on my laptop. So.
Yeah. So the question maybe to rephrase it is, how can solo or PhD student researcher live in this side over here, while this side requires a lot of compute? I think that's a really good question. There are some solutions to that. As PhD students, you can get Amazon Compute. You can apply for that, and often they will grant you a good amount of compute. Your faculty can contact places like NVIDIA and so forth to get a lot of GPUs. So you can work with them on that. Definitely, it takes some effort. But I think it's possible to get out here. You can also intern at some of the other places, see what happens with your ideas if you run it on their compute, and then take the findings from there. So there's a few things. It's definitely true that the more you go here, the more compute you have, the easier it is to live over here. At the same time, even if we want to be over here and want to solve, let's say, complete digital worlds or even physical worlds, it doesn't mean that the way to develop the ideas behind what's happening here is by right away jumping into solving the most complicated environments. You'd still want to design distribution over environments, not a single fixed environment, because then you're back to mastery, but you want to still design something that's as small as possible, yet meaningful in this context, rather than just trying right away to solve something huge. Question there.
I think we're going to get to this, but do you think that code gen is a necessary step, or is it better to just keep everything like soft and black boxy?
So this is one way to do things here. What I would say that maybe the way I think about it in my head, something like this, is that if you think about maybe the architecture of a neural net, you could decide that the architecture is still fixed, but you just learn the parameters, which happens in RL squared, which we'll talk a bit about. And then the next level would be something where the architecture is not fixed anymore. And when the architecture is not fixed and where you're learning the architecture, you're probably not learning the architecture at the level of every individual edge, but you probably have a more compact representation. That's some kind of grammar that generates architectures of a certain flavor, where there's maybe, probability of connection between neurons that are this close to each other is this high, this far apart, probability of connection is that high. And then I think of that as the underlying code representation that is a compact way of encoding the architecture that you might be working with, rather than thinking of it as going back to this kind of code that's coding solutions to problems. In terms of compute, which definitely is also just what the question that came up, the reason I think we can go more and more to the right here is because there's a very dedicated effort for building neural net specific compute, which is the architectures that are most easy to optimize currently. And what that means is, with these dedicated efforts, that it's likely that within the next year or two, we'll go from compute we have today up by a factor maybe 10, 100, or even 1,000, which is much faster than any increase in compute we've seen in recent years, which will make us leap far to the right a lot more quickly. And the reason we're going to see that acceleration is because there is dedicated hardware being built for the kind of compute that's happening here. It's not that people know how to pack transistors more densely all of a sudden, that's hitting its limits. But the prior architecture, CPUs, GPUs, are not exactly the perfect architectures for the kind of compute we want when training neural nets. And these will be dedicated to that, and as a consequence, a lot more amenable, and we'll get big compute speed-ups. People have actually been starting to look at this for a while. One domain in which you can do learning to learn is optimization. Rather than designing gradient descent, stochastic gradient descent, should there be some accelerated gradient descent, should it be momentum, and so forth, just let a neural net figure out, an LSTM often, what the optimization procedure should be. You can do this for classification also. You can see if you can learn to classify. If you are faced with many classification problems in the past, can your neural net be ready to more quickly solve the next classification problem? We'll revisit that a little bit later. Or generative models. Can you have a neural net be such that it's ready to learn to generate new characters of a certain type very quickly from only one or a few examples? What I want to focus on here, though, is the reinforcement learning side of things. So this is our starting point. DQN learns slowly, gets a good policy, learns slowly. Same is true for the policy gradient methods compared to how fast humans learn. The starting observation is that the methods that are currently state-of-the-art are fully general algorithms. And they can solve any Markov decision process that you could possibly mathematically define. That's nice that they're so general, but what you encounter in the real world is a small subset of what is mathematically definable. And so maybe, this is just a hypothesis, but maybe humans can learn more quickly because they are attuned to Markov decision processes that happen in the real world, and as a consequence can zone in on solutions to those problems more quickly, even if they cannot solve every possible mathematically definable Markov decision process very quickly. So then the question is, can we design, or it's going to be learn in this case, but design might be fine if you can do it, fast RL algorithms that take advantage of this, that you don't need to solve every mathematically definable problem. So what that would mean then is that effectively what you have is a distribution over MDPs. So, and we'll sample from that distribution. So M is a sample MDP from a distribution over MDP. So what we want is somehow, when we get a sample from that distribution, to be able to solve it very quickly. So we have an expectation over MDPs, an expectation over trajectories in that MDP, and then expected reward accumulated along that trajectory when we use an RL agent parameterized by theta. And this RL agent could be anything as phrased here. In practice, for us, it'll become something more specific, but think of it as just any agent, any piece of code, any neural net, whatever you want to put there, that will get to enter an MDP, in that MDP, act multiple times. So it runs one episode, another episode, then it's over, goes to another MDP, and repeat. And you want the agent to be good at this process of being dropped somewhere, get a few attempts, and somehow have collected a lot of reward in those few attempts, and on expectation, optimize that criterion. Any questions about the criterion here? Because this is what we'll be working with for the remainder of lecture. Yes?
I just have a question about the assertion on the previous slide. Like the
Which one? The compute one?
The second bullet. Yeah, no, that one you just.
Okay.
So why do we think that there's a very, very tiny subset of MDPs that could be defined that are encountered in the real world?
So physics of the real world is one type of physics. So that's already constraining things a lot. The way everything works, I mean, you could, if you mathematically say how to go from current state to next state, you can define it in a very open-ended way, and there are so many ways that you could define it if you just allow you to put any function there, and physics actually constrains it quite a bit to what happens in the real world. So that's one part of it. That's on the physical side. If you think about computer games, the way games are designed, there's a certain art that goes into designing games and structure into it, and it's never completely random. It's actually people inspired by things they've probably seen in the real world in other games that give every game a somewhat related structure, compared to if you just had completely random transitions from, let's say, what you see on the screen now to what you see on the screen next, and so forth.
But don't all those algorithms rely on the various structures that come about in each of those MDPs, and they learn from them in some way?
So what they do, if let's say you have a PPO or something, you run it, what will happen is you put it in front of a game, it'll learn to play that game. And it'll absolutely exploit all that structure to find a good policy. And that policy will be, sorry, it will not, but the policy will exploit the structure. But the algorithm itself will not exploit the structure that is in the games. It's only when the algorithm is converged that the policy it finds exploits it. But the algorithm doesn't anticipate it, doesn't get ready for it. Now, people will do things a little bit in this direction, in that they might say, I'm choosing a neural net architecture that I'm training up that has convolutional filters and so forth, and then that is putting a little bit of prior information about locality of, if you have a big image, you can understand what's in the image based on looking locally and expanding from there. You don't need to, look at a weird combination of 10 pixels that could be in arbitrary places on the screen. A competent would not be able to figure that out because it's not architected that way. So definitely people in the architectures do a little bit of this. What we're hoping to do is maybe go beyond that, not just have the architecture have a little bit of a prior, but also the algorithm that optimizes the parameters take advantage of structure that exists, and maybe do that in a data-driven way rather than us needing to think through it. Carlo.
Might there be a possibility that you can pre-train a system so it deals well with physically plausible situations, and being pre-trained that way, if then let loose on video games that mimic physics in some way, would be much more efficient to adapt to that particular fine-tuning of the physics for that system.
Yeah, so the question was, can we somehow get things pre-trained so they're ready to do other things later? And that's exactly what this objective will do for us. So I haven't shown it yet, but when we train this, what we're going to do is we're going to have a set of training MDPs and optimize our agent on the training MDPs such that when later another MDP gets sampled that it's faced with, it would hopefully also be very fast at adapting in that new environment. So that's it. You're exactly formulating what we're going to be looking at. Yes?
So between different MDPs, they might have very different state, action space.
Yes.
Different sizes and such. How do you handle that going between MDPs?
I haven't seen any current work that handles that. The current work when looking at distribution over MDPs tends to be more constrained. And we'll see examples later. There are ways to do it in principle. I haven't seen anybody do it. You could have architectures where, let's say if you want to control different robots in Mojoko, and you want to have a distribution where the robot's not always the same, you could have a maximal number of motors that are present in your robot, and always have access to that maximum. It's just that sometimes half of them don't do anything because they're not attached to a robot, because this robot only has 10 joints. It doesn't have all 20 joints that another robot might have. And it might be able to pick up on that. Nobody has tried that as far as I know, or nobody has at least published something about having tried that. Another thing that you could do potentially is have a attention model to deal with this. So you could have a robot, and you could decide that your architecture is such that you pay attention. You can decide which motor to pay attention to. And that way you automatically have something that is independent of the number of motors in how your architecture functions. So there's a few things you could do, but I haven't seen, and there might be many more things, but I haven't seen anybody actually try this out and report results on it. So the hope is that if we train an agent that is good at, on expectation, doing well over capital K rollouts in a sampled training MDP, then the same thing will be true for test MDPs. At this point, we're actually putting reinforcement learning on par with what people do in supervised learning. In supervised learning, you have a training set on which you train, and you hope it'll still do well on the test set. Most reinforcement learning work doesn't do that, doesn't have that separation, just trains, and it says, here's how well it became, this is the result, and done. The counterpart in supervised learning would be that you just train on the training set and then say, look, we got this percentage. Look at us, we got 99%. That's not how it works in supervised learning. In RL, sometimes it's okay, because all you need is master a skill, then that's fine. But this is making generalization matter even more. We want something where, after having trained on training MDPs, you can deploy this agent in a test MDP, and it can adapt quickly in that test MDP to do well there. Now we have to choose what to put underneath. In the first part of the lecture, we'll put a recurrent neural net underneath. What's a recurrent neural net in terms of how we think about it here? A generic computation architecture. It's something that can compute and store things. The hidden units where you store things, and then the weights are deciding what you compute based on what's in the hidden units and what's coming into the sensory modalities. What this also means that if we change the weights in the RNN, we are actually changing the reinforcement learning algorithm that lives inside this agent. So let's think about this very explicitly. We have an agent. This agent is a recurrent neural net. It's going to take in current observation and output an action, and it'll see then what reward came out as well as what's the next observation. The weights in the RNN determine how that information is processed. That's exactly also what a reinforcement learning algorithm would do. A reinforcement learning algorithm would look at observation, see what action was taken, then what observation came back, what reward was associated with it, and based on that do an update to the agent. Same thing happens here. The weights will, based on the weights, you'll get processing, and then the hidden units will change. And so the hidden units effectively encode the policy the agent is currently using, whereas the weights encode the reinforcement learning algorithm that's updating that policy. Then the way we optimize the weights is this is still a reinforcement learning problem as a whole, so we can actually optimize the weights by running an existing reinforcement learning algorithm that will optimize the weights in the recurrent neural net, and the result is a recurrent neural net that encodes an agent that inside of the agent runs reinforcement learning also. So the final result would be hopefully a fast reinforcement learning agent that is expected to do well in new MDPs it hasn't seen before. So explicit comparison in reinforcement learning. Slow reinforcement learning algorithm will, based on what happens in the environment, update the policy, which interacts with the environment directly. In something like RL squared, reinforcement learning is still on the outside up here, but it's also on the inside here. We have a recurrent neural net policy that takes actions, gets to see observation and reward, which is different from over here. Standard RL does not give the policy the reward experience. That's an external event. And then the external RL algorithm updates the policy. Here, the reward also goes into the RNN. As a consequence, it can run an internal RL algorithm to adapt quickly to whatever environment it's in. And so that box there, the RNN policy, is hopefully at convergence the fast RL agent. And the result here is mastery of learning to do well in new environments, not just mastery of to do well in one new environment. So how to evaluate this? One way to evaluate this is to look at problems that people have designed very good reinforcement learning algorithms for by hand and see how well learning to reinforcement learn compares to the best hand-designed algorithms. Bandits are where you have a bunch of choices available to you. Each choice corresponds to a distribution over possible payouts, but you don't know the distribution ahead of time. So you need to explore, try different things, and see where the highest payout is, and then repeatedly start pulling that one. There are provably optimal algorithms for this. Gittins indices give asymptotically optimal performance. There are computationally cheaper algorithms that get pretty close to Gittins index performance. So let's take a look at how they compare to RL squared. RL squared is the learning to reinforcement learn. We see that it actually performs about as well as Gittins indices, which are asymptotically optimal, which is amazing, because what that means is that with just this simple learning to learn approach, we ended up discovering a recurrent neural net that encodes a algorithm, a bandit solving algorithm right inside the recurrent neural net. And other ways to get there actually was many, many years of research for people designing all kind of different ways of trying to solve these problems. And right now, that's in some sense directly superseded by just learning to learn. There are learning curves for this too. So what we're looking at here on the horizontal axis is meta-training iterations. This is the recurrent neural net is being trained here, is being faced with one problem after the other, after the other, after the other. The weights in the recurrent neural net get updated, and you can see how good the recurrent neural net becomes after a certain amount of training. So here, it takes about maybe 50 iterations for small bandit problems. To solve them, it takes a little longer for bigger bandit problems. And then if they become very big, it actually takes even longer, and it doesn't fully get to the Gittins performance yet. Yes?
Just to clarify, how are you parameterizing like the actual policy?
How is it being parameterized?
Yeah, like what is the actual, like how, like you edit the policy using the learned RNN, but like what is the actual policy?
So the policy you cannot access in an explicit way, the way you would see in a regular reinforcement learning setting where you just have, let's say, a neural net that is your policy. Here, the recurrent neural net is kind of an all-in-one. The recurrent neural net has encoded a combination of what the current policy is, as well as the reinforcement learning updates. The computation of the reinforcement learning updates are effectively encoded inside the RNN. So you cannot just tease apart the policy. You can observe it. You can let the RNN run, and you'll see that your policy is constantly changing based on what it's seen so far. And so the way to think of it is that the RNN encodes an extremely adaptive policy that starts out doing something, but then from the experience will update itself again, become better and better over time in the current environment it was put into. The specific here, it's just a big LSTM. I forget how many units, but it's just one big LSTM that encodes the full agent. So we have an agent encoding rather than a policy encoding here. Yes?
So for the biggest case, the 550, is it underperforming just in case the model itself doesn't have enough capacity? Like if you put more units in it, do you expect it to be closer to the Gittins index?
So not sure about that. Actually, let's see. Actually, it's a solid question. So the things we tried to get at that, one thing we tried is we have the Gittins index, so we can actually play a Gittins index. We can train the RNN to behaviorally clone the Gittins index policy. Yeah. And actually, it's expressive enough to clone that policy. So it has the expressiveness to encode that. But the question is it expressive enough to learn to get there is another question. And that's hard to know, because is it expressive enough for that, or is just the outer RL algorithm not good enough? I think we ran PPO or TRPO on the outside. Maybe it wasn't giving it enough signal. Maybe the problem is so big that the signal comes over long horizons. So what happens here is that this is a 500 horizon problem. So you get to pull the banded arms a total of 500 times, which is a very long horizon problem compared to, let's say, 10 or 100. And so you need to optimize to be optimal. There's a lot more to optimize over when there's a longer horizon. And so that signal might not come through. And so what it might just be is that it's actually underfitting. Because you can't really overfit here, because in some sense the train and test data are almost the same, because you don't need to have a finite training. I mean, it's a continuum of banded problems. You can just any time pull a new banded problem, and then when you get that test time, you just pull another new one. And so it's not, you can't overfit in that sense if you're always pulling a new problem. But you can underfit, and clearly it's underfitting. Yeah. But is it the architecture, or is it the slow RL algorithm on the outside? Not clear what's causing the underfitting.
Okay, interesting.
Yes?
So if you can just pull up these additional banded settings, right? What stops you from splitting those settings into several settings and then doing RL cubed or something?
Yeah, you should try it. Final project for the class here. And you could...
like, does it get harder to learn as you go up in this hierarchy?
I don't know if anybody's tried it. I think it would be worth trying, where you just repeatedly do this, where you say, okay, clearly over this horizon we don't get enough signal, but maybe if we first train on a shorter horizon, and somehow from that, tricky part is you need to get a fast RL algorithm to put on top of it that is somehow generic enough to still train this. I mean, this relates a little bit to the question about where's the policy, how do you pull it out, and so forth. It's not obvious when you train on this how you would then say, now I have another thing I can layer on top. That's not obvious. What you could do is things like you could train on this, and then you could anneal it out to 500 and see if gradually, by training on smaller problems first, it might be able to solve bigger problems. And maybe it's possible it'll get there. Not obvious to me. It would have to be tried. You can also try this in locomotion. So in locomotion, what would be the distribution over task? Let's say you're looking at half cheetah, which is a two-dimensional locomotion task. You'd say, well, the task distribution is desired velocities. So a new task means a different desired velocity. And then the reward could be maybe squared distance from the desired velocity. What do you expect to happen with something like RL squared? Ideally, what it would internalize in this RNN is that after it takes 1 or 2 steps with a cheetah, so it would internalize that it needs to do something where it moves, let's say, and have some basic notion of how to move, but then decide how fast to move. It should take 1 or 2 steps. It sees the reward. It processes that reward and says, OK, clearly right now we're in the 5 meters per second task, because I was going 1 meter per second and the reward was this much. And then I'm going to immediately latch on to that task and start running at that velocity. And that's actually exactly what happens. So this thing doesn't even need a whole rollout to learn anything. Just a few time ticks into the first episode, it's already doing the right thing that you're asked for at very high performance. Here, running at speed 0, running at speed 0.5, and so forth. So what that means is that at training time, it invented a variety of gates that are effectively stored in the weights of this recurrent neural net. And then when it's faced at test time with a new task, it can activate hidden units such that it'll start doing things corresponding to the reward function that's chosen. Same thing for Ant. It learns to master each task almost instantly within the first episode. This is very different from regular reinforcement learning, where you'd run for thousands, if not millions, of time steps before you would get any kind of locomotion. Of course, this is a very narrow task distribution. Earlier was a question, what is the task distribution? What if you have different number of joint angles and motors and so forth? This is a fairly narrow distribution, but it's a really nice proof of concept that if the distribution is not too wide in terms of what's possible, this can work really, really well. Here's a more difficult one. Let me go through this example, and then let's see if there's still questions. So here, the agent is supposed to, it will always be dropped in a new maze. It will not have access to the map of the maze. That's just for our reference. It will be dropped in a new maze. There will be some kind of target that's bright red. It gets to see just monocular images. It gets to turn 2 degrees to the left, 2 degrees to the right, or keep going straight. And somehow, it has to figure out how to get to a goal in that maze. So intuitively, what we hope would happen is that when you train up this agent, it becomes an agent that has internal capabilities of reliable navigation, not bumping into walls, but running down hallways effectively, internalizing a map of what it's seen so far, such that it can consistently explore, not just randomly explore. And then if it gets dropped in the same maze again, that it would remember how the maze worked the previous time and follow the shortest path to the goal in that maze. And in fact, that's actually what happens. So here's what you get with just random motion in this maze. It's not going to do much. And this is what the agent gets to see. This is what happens at the very beginning of the meta-training process. Then after a lot of meta-training, the recurrent neural net becomes better and better and better. And then when you drop it in a maze, it is very good at navigating down hallways, looking around corners, doesn't run all the way down, and knows the red thing's not there. Here it sees it, goes to it, gets dropped again, and it goes straight to the destination. Here are some numbers on that. There are small mazes and large mazes. What is shown here is the average episode length. The shorter length, the better, because the episode ends when you reach the destination. And so episode 1 in a small maze takes about 52 time units. This episode 2, only 39. What that means is that when you get dropped in the same maze a second time, you have stored some information to speed up the second time you're navigating that maze, and then it doesn't really improve much from there, which means that in the first run, it collects all the information it needs to do well in all remaining ones. Similar for the larger mazes. Then here we analyzed how often is the second episode better than the first episode? For small mazes, 91% of the time. The second episode, it gets to the destination faster than the first episode, which means it learns something and does better. And then in the large mazes, it's 71% of the time. Still have a question?
Yeah, I guess I had a question about the Majoko environment you were showing. You were saying that it learned like, a suite of policies, like, run at 0.5, 1 at 1, etc. So during the training process, like the meta training process, did it get each of those tasks beforehand, and so it learned each gate, or did it like?
So at training time, meta training time, it gets randomly sampled. Well, it's always in the same physical environment, but there's a random variable which is what the reward function is, and so that's a real number, and that real number is always going to be different. And so at training time, meta training time, it gets to try out on a lot of different reward functions and gets very good coverage of the space. And it clearly learns the gates that are needed to cover that space. At meta testing time, it starts going. It immediately notices from the reward function what it is that is actually it should be doing, and then adjusts its gate.
So it's able to like interpolate among learned gates or something like that, or?
Yes, it is interpolating in that. There is no extrapolation. So training time distribution of possible desired velocities is the same as the test time distribution, but the exact samples will not be the same.
Right, yeah. Can I ask a question?
Sure, yeah.
On the maze doom examples, on this results where you're saying that, like on the first iteration, it explored the maze and found the goal. On the second iteration, it just went right to the goal. did you do any tests where you had an agent that learned, on the first iteration, and then, solved the maze for like the future iterations, then put it in another maze, and then maybe like after he did that one, brought it back to the first maze and see if it remembered how to solve the first maze after like...
Yeah, that's a good question. We haven't done that. If you did that, you'd probably also want to design your mazes a little differently. So these mazes are designed in a way that there's literally no identifying information anywhere on the walls. If you're going to do something like that, you probably want mazes where maybe there is some, paintings on the walls, such that as you are in a maze, you're like, oh, I remember when I see the painting of this and this person or this and this scene, I'm in maze number 5, and I remember the map, and now I can solve it more quickly. But that would be a very interesting experiment to run. Here are the meta-learning curves for the maze navigation. What this is showing is that about a little more than half the time it trains successfully, but the other half of the time it doesn't. So actually getting the meta training to succeed, again, what you have here is an underfitting problem, that it doesn't always succeed at fitting this RNN to succeed at this task. So still definitely some challenges there. So quick recap. What we looked at is a formulation where there's a distribution over MDPs rather than a single MDP you're trying to solve. And what you want to do is you want to optimize expected reward when you get dropped in a new MDP and when you get to run capital K episodes in that new MDP. The agent is a recurrent neural net. It's a generic computation architecture where the different weights in the RNN correspond to the agent internally having a different reinforcement learning algorithm and different activations corresponding to encodings of what the current policy is. The meta objective here, that's shown at the top, is still optimized with a slow reinforcement learning algorithm, though maybe RL cubed will stack things on top and on top and top again, and no need to stop at cubed, of course. We'll see. Now, this is just one choice. So the objective might be not less debatable what you want to do there. It's like, okay, I want an agent when dropped in a new environment does well, but putting an RNN there is actually just one specific choice. And maybe you want to put more structure into the agent rather than just a generic RNN. Just like people don't train maybe fully connected networks for computer vision because a fully connected network doesn't have enough prior information, makes it harder to pick up on signal at times than if you architect more what goes into the network. So let's take a 2 or 3 minute break here, and then after the break, let's look at what we can do to put more structure inside these networks. Do you have a question?
So
Okay, so basically, from like what I can tell, you basically have created sort of like the controller part of like a brain, right? So I guess like ignores like other sorts of parts. But so I guess like the question is like in brain research, we're like trying to like pick out like the individual components. All right, this does this, this does that. So do you think it's worth trying to interpret like what these models are learning, or do you think it's better to just like learn an architecture that like
I think
is
it's
better?
no. I think both are good. Let's see. I think both are good. For more careful designing the architecture underneath, we'll talk a little bit about that, but it's not even close to what would be a final architecture. For analyzing what they're already doing, some people will do things like, can we regress from, let's say, certain hidden unit activations to certain meaningful quantities. So let's say you can do a linear regression from the activations in the LSTM to the coordinates of where you are in the maze, then, or some subset of the hidden units, then that indicates that that subset somehow encodes something about where you are, and then there's some explicit encoding of locality. And so those kind of things are, I think DeepMind is a paper that look at this a little bit. It's very similar to the RL squared paper. It's called Reinforcement Learning to Reinforcement Learn, something. And they look at some of the neuroscience interpretations. That is, I think, exactly what you are thinking about. And they published it in the neuroscience venue. I forgot, cognitive science something or neuroscience something.
Great.
So the first author is Wang.
Cool, thanks.
Yeah. Hey, Carlo, how are you doing?
So, if you take the traditional approach of 3 or 4 years ago, you train a Pong game, and it's really good, then you rotate the screen 90 degrees.
Doesn't work anymore.
It has to completely learn from scratch. So it's the new approach where you have the meta training before. What would be the speed up now after you rotate the screen 90 degrees? Is there a noticeable speed up that you get from the meta training or the pre-training?
So you want a somewhat wider distribution, so at training time you can reflect the variation at test time. So let's say there was a continuum of rotations, which of course with pixels doesn't really work. But if there were a continuum of rotations and you see some subset of them at training time, and then at test time another subset, it's likely this will pick up on the game really quickly.
Okay. But if you only have it trained that way, I mean,
no, you need a distribution at training time. If you only have for this approach to work. I'm not saying in the long run that's what's needed, but
so if we have variations of training games where the aspect ratio is different, all of that, but they all handle balls and paddles. Is the notion of balls and paddles and physics of trajectory somehow learnable?
So that would be a good one.
So you can then really
let's say you set up a game where the goals might be in different places, where there might be obstacles in the middle and so forth. It should be able to adapt to a new one very quickly.
Of that. So can it learn the abstraction of that and then apply
I haven't seen anybody try that, but I think it would. And that's exactly the idea.
Real good demonstration.
All right, let's restart. Any lingering questions from the first part? Okay, so can we put more structure into the agent? I'm going to go over this one a little more quickly because I think you covered this already at some point in class, but I want to tie it into what we've just seen. Let's say you traditionally run an RL agent and has a policy pi theta currently, and you run a number of episodes B. Then after you completed your batch, you might do a gradient update, change your policy, and go again. And then maybe that new policy is better than the previous policy, and maybe even do this multiple times. But the simplest case, you would just do one update. And so this delta theta is then classically obtained through some standard reinforcement learning update, maybe PPO, TRPO, A3C, and so forth. One thing you could do is you could say, if I want an agent that adapts quickly, how about I find a theta such that I know in here, in my next episodes, I'm going to do reinforcement learning updates. I hard code the reinforcement learning algorithm that lives in there, but I'm going to encode it prior over policies by choosing theta such that an adaptation leads to very good performance right away. So we try to find a theta such that an agent that runs a known reinforcement learning algorithm does well at optimizing reward in a new environment that is a good adaptive agent. This approach is called model-agnostic meta-learning. Some work jointly with Chelsea and Sergey that was the first paper on this. So you have some pre-trained parameters, then you take a standard gradient step, you get new parameter, and you hope that that new parameter actually does well. So the loss here that we ultimately care about is the loss in the new parameter after the update. Get some experience, update, how well do we do after that? So if you have many, many tasks, you can then try to train a theta such that whatever new task you encounter, you get very good performance after one update. Pictorially, what you can visualize this as is that there is some parameter space theta, very high dimensional, where theta lives in. Different tasks will have different updates they want from theta, and they will have different optimal settings. But these different optimal settings might be not too far apart. They might be able to find a theta that lives somewhere in between, and from which one update is enough to jump onto optimality for each one of the other tasks. OK, so you can actually consider the same challenge problems as we looked at before. This one here is the AND problem. This is what happens if you just do some pre-training on all tasks that you might want to consider in terms of running around. So the resulting theta is not optimal for any one of them. It's just some kind of average of some type of what the optimal thetas are. And you don't adapt super quickly to the task. If you watch this again, adaptation is, so there's the initial policy, and then after one gradient step, it's supposed to go at velocity 0. It's not exactly doing that. Velocity 3, not exactly doing that. So just averaging the theta that you get from training for multiple tasks is not that great. But if you explicitly optimize your theta such that after one gradient step, it's a good theta, actually you do really, really well. Now, if you compare with RL squared results, this one needs to first do an episode and then does an update. RL squared will identify instantly after the first time step what it's supposed to do and nail the task. So it's a different setup, but both within their own context do really well at solving this task. Same for Cheetah. So at the top here, what we're watching now is if you randomly initialize the neural net parameters for Cheetah and then do some gradient updates, it doesn't really become all that good. It does, in fact, some weird things that are far from optimal. But if you train with MAML, you land at a parameter vector theta such that after your first batch of rollouts, you do one gradient step, and you're already optimizing for the current reward very effectively. So what we've seen here so far is that we're reformulating the reinforcement learning problem as not just about mastering one current task, but rather somehow finding an agent that is good at being dropped in new environments where it can quickly master whatever needs to be done in that new environment. This agent will get, in this case, 2 episodes in a new environment and hopefully did well by the end of those 2 episodes. We've seen a black box version of the agent and a version where we hard code the reinforcement learning update, but still can train what the parameter vector theta is from which everything starts. There are other architectures you can choose. And these are definitely not the last ones either. But let me tell a little bit about a few variants here that are outperforming the ones we already saw. The simple neural attentive meta-learner looks just like RL squared in some sense, but instead of having an LSTM, it has a combination of a wavenet that is a dilated temporal convolution and attention. So why did we decide to investigate this direction? If you look back at the learning curves for RL squared, trying to train up the LSTM to become a good adaptive agent, often it was underfitting, meaning it was not getting enough signal. People have seen in sequence-to-sequence tasks the same thing happen. And WaveNet, which was invented about a year ago at DeepMind by Aaron van den Noord and collaborators, what they notice is that instead of using a recurrent model, if you use a dilated temporal convolution, which is just a convolution, but where you skip over things in a hierarchical way, then you can actually get signal from much further back, bring it in. Now, the issue with just using a dilated temporal convolution is that you don't get a whole lot of detail from the past, because it kind of branches out and becomes more and more coarse the further you look back. So what the attention does is that the dilated convolution allows you to look back, and then tension then allows you to go look at all the details at specific times that the dilated temporal convolution told you to pay attention to. And so you can still get all the detail where you want it while looking over a long trajectory in the past. When doing that, it turns out you can pull in more signal than when using an LSTM. And we compared performance. This is on the bandits problem. Snail, the dilated temporal convolution plus attention, does better than the LSTM, which is RL squared. They all do also better than mammal. Then for tabular MDPs, just small discrete MDPs, snail also outperforms LSTMs and mammal. So what it means is that it's just compared to mammal, mammal has less expressiveness, so that could be the reason it doesn't do as well. It doesn't have the same expressive capacity as the two others. Between LSTM and snail, it's really largely a matter of that LSTM is not able to pull in the signal, whereas snail is able to pull in the signal. Here are some of the learning curves that also indicate this. It's not just that snail gets to a better level, it also just pulls in the signal more quickly, is the red curve, than if you use a LSTM. Here's the ant and cheetah. We're comparing the LSTM, which is RL squared, with snail, the simple neural attentive learner, which is red, and then mammal in green, and then the oracle, which is a policy trained for the exact task you're trying to solve, fully trained. And what we see here is that snail consistently does best, often tied with LSTM, and they all outperform mammal for these tasks in terms of speed of learning and also final performance within that number of rollouts. We also revisited the maze navigation, small and large mazes. We see that the trajectories snail finds are shorter than the ones the LSTM finds, which means it does better. Lower is better here. So it again is able to extract more signal and to do quite a bit better than the prior work. Here's an example of the kinds of mazes. The mazes have become bigger. Here is the first rollout. The agent starts here. Of course, it doesn't have the map of the maze. It just starts wandering around, goes here, 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 circles around, explores the maze, sees the blue, goes there. Second drop in the same maze, it goes shortest path to the destination. Also turns out that this is not restricted when you think about mammal or snail to reinforcement learning. There's nothing specific about reinforcement learning when you say, I'm looking at some past data, and based on that, I'm supposed to make a good decision right now. If you think of classification, let's say you've never seen a segue before, you see it for the first time, you might instantly learn a classifier for what a segue looks like. That is a very similar problem. People have standard benchmarks for that, Omniglot and Mini-ImageNet. Mammal, when it came out, was state-of-the-art. That was back in February, outperforming much more specialized approaches to classification. So that was really interesting. A lot of people had built specialized classification meta-learners, but Mammal just uses a gradient update and pre-trains the neural net to be ready for gradient updates to be successful, was outperforming all the specialized approaches. Since then, Snail actually has outperformed Mammal on all these tasks. So what we see here is two very generic approaches that can actually do the best on a fairly specific task, namely classification. Carlo?
In the second drop in the more complicated maze,
yes.
How did the agent know where it is? So it could go very directly.
So here, in this experiment, it knows the second drop will start in the same location as the first drop. And that's why it knows to go directly there. There's another version you could run where it would be dropped in an arbitrary place and then have to first localize itself and then go to the target. That's not what's shown here. Same is true for few-shot classification on Mini-ImageNet, where Mammal, which is this one here, was state-of-the-art back in February when it came out. But at this point, Snail outperforms that by quite a bit. There's a lot of choices you can make architecture-wise. So far, we've seen 3. Here's another one that tries to more directly address the notion of trying to solve problems that have very long horizons. If you look at reinforcement learning problems and what people have been able to solve, most of them, if not all of them, have very short effective horizons. Meaning that if you optimize for a horizon of 100, it's good enough to solve the problem. It might be that the problem has a horizon of 1,000 or 10,000, but if you ignore that and just have a discount factor of 0.99 and you still solve the problem with a discount factor of 0.99, that means that effectively the horizon of the problem is not 10,000, it's really just 100. That's the case for almost all successes. And so what we wanted to look at here is, can we look further ahead than just 100 time steps? The way we formulate this is that we said there's going to be two levels of decision making. You get in observations, then there's a master policy which chooses a master action which decides which of the low-level policies is being activated at the current time, which then gets the action executed. So this architecture is saying, I want there to be low-level policies such that just selecting between those low-level policies is good enough to solve tasks. And then what you could do, is you could let the low-level policies, let's say, run for 100 time steps. So you make one master-level decision. The low-level policy runs for 100 time steps. Then you make another master decision, repeat, repeat, repeat. Now a 10,000 horizon problem becomes a 100 horizon problem for the master policy because of the factor 100 you get from the low-level policy executing for 100 steps every time. Yes?
And those 100 and 1,000 numbers are set by you as hyperparameters?
This scenario, yes. We're choosing how long the low-level policy acts, and then that high-level policy just, whenever that horizon has ended, takes a new decision. So then the question becomes, how do you even decide what goes into the low-level policies, what does the high-level policy need to do? And that you can actually formulate as a meta-learning problem again. So you can say what we want is, we can think of this as an agent. And when we drop this agent into a new environment, we want it to be able to learn to do well. So we want it to be the case when you drop this agent in a new environment that it's never been in, is going to, over just a small number of episodes, be able to learn to solve that, where during those episodes, it only gets to update the master policy. It doesn't get to update the low-level policies. So what that means then is when you're doing meta training, you're discovering low-level policies. If this works out, that's the idea. If this works out during meta training, you're discovering low-level policies that are good for you to be able to reuse as is by simply selecting between them when faced with a new environment. One test environment we looked at is moving bandits. So we've seen bandits. In moving bandits, there is, in this case, two bandits. It's just like regular bandits, depending which one. You don't know the distribution over payoffs for either one of them. You need to discover which one has the better payoff distribution and keep visiting that one. But in this case, they won't always be in the same place. And so what you'd hope to emerge here, and the kind of behavior that we get out, is that the low-level policies are about navigating to one or the other for the other policy of the bandits, and then the high-level policy chooses which bandit you want to navigate to, and then explores at the level of just standard bandit problems, whereas the low level needs to take navigation actions. We see here, look at the full training, you can see that the meta-learning shared hierarchies approach actually does quite well. A standard RL squared approach actually ramps up pretty well, but then it's a little unstable and starts doing poorly after a while. Maybe needs some more tuning to get that to work, but either way, it's ramping up more slowly than this more specialized architecture that we're looking at here. Then, when you're in an actual new situation, how many gradient updates do you need of the master policy? Very few. It adapts very quickly with this new approach. Whereas if you just have a single policy you train, well, it needs to learn from scratch. It doesn't really go anywhere. Shared policy across different tasks does something in between the hierarchical version. This is the 4 rooms task. I don't have a picture of the 4 room task, but what it is, it's a bit like a house with 4 rooms. It's a standard hierarchical reinforcement learning challenge task. And so we use this task to compare with option critic, which is a very standard hierarchical reinforcement learning algorithm. And we see that option critic doesn't do nearly as well as this meta-learning approach to hierarchy. A few other experiments we did. This one here looks at, can you invent different gates? Let's say running north versus east for ant, or actual running versus crawling for humanoid. I think this is one of the most interesting results here that came out, is that we trained the ant in a variety of mazes, and the task was maze navigation, getting to a destination, and the low-level policies that emerged from just the reward being about maze navigation was 3 different directional movements for the ant that turned out to be very helpful for a high-level policy to rely upon to navigate mazes. So here's an example of that in action. We see zoomed-in version of the ant over there. We see which of the sub-policies the high-level policy has chosen. It can solve, in this case, I think, a Horizon 3000 task, which with regular reinforcement learning would stand no chance. There's an enemy there. If it gets in that zone, the enemy can hit it. But it turns out, actually, even though we thought of it as an enemy, what we found is it actually leverages the enemy to get a faster locomotion towards a destination. And the enemy helps it get there more quickly than it otherwise would be able to. So in a little bit of time we have left, I want to say a bit about how maybe this meta-learning could work out for real-world things. It's a lot easier to work in simulation. Everything I've shown you meta-learning-wise has been in simulation, because even though it adapts very quickly, it actually still needs to meta-train for a while. And so meta-training in the real world might be tricky. Simulation, you can build maybe realistic simulators. Maybe you can build something that understands a translation between simulation and real world. Or what seems most promising to me right now is to do straight-up domain randomization. The idea there is that you just introduce enough variability in your simulator such that the real world would just be another variation. But it's not just another variation in the results that we look at here. None of the simulated rendered scenes look exactly like what a real-world scene would look like. It has notions of the real world. It has shadows. It has variation in where the light is coming from, occluders, viewpoint changes, but nothing looks like a real image. The beauty here is that these kind of things can be generated super, super fast. So rendering these simple scenes is very, very fast compared to rendering realistic scenes. And it turns out that what we're hoping for is that if you train on these scenes without ever having seen a real-world picture, to still get the right answer of localizing the object that you might care about. It's actually inspired by some work Ferejde and Sergey did in the context of quadcopter flight, where they were looking at, can we train a quadcopter in a simulated hallway environment and then deploy it in the real world and still have it work? And actually this here is a deployment in Corey Hall, just across the street, of a quadcopter that was trained only in simulation and is reliably flying down a real-world hallway. I mean, there's a slight subtlety to only train in simulations that it was a network pre-trained on ImageNet in this case, and then after pre-training on ImageNet, trained in simulation only, and that was good enough. We decided to look at how to scale this up a lot more, have more randomly generated textures, have the rendering be even less realistic than what they had to make it even faster, and also not pre-train on any real images from ImageNet, just completely in simulation. It's a standard ImageNet-like neural net that's being trained that outputs the pose of the object of interest. And so what you see here is actually the robot using the vision system trained only in simulation, reliably picking up the block of interest, which is the rectangularly shaped block. If you look at the learning curves, number of training examples in thousands of images, you see that the error nicely goes down. We compare this with what if you pre-train on ImageNet, which maybe you think would help. What if you pre-train on ImageNet? You have some interesting notions to start from. Sure you do, but actually it doesn't help for that long. After about 4,000 images, rendered images, it's already a tie between the two. And then at the end, it's still a tie. So you don't benefit from this pre-training on ImageNet. So the way I see this tie into the meta-learning is that one scenario we could pursue is you meta-learn largely in simulation or entirely in simulation. you get an agent that's really good at adapting to any simulated environment. And then the hope is that when you drop it in the real world, just like this classifier or pose estimator could just generalize to real world, that this agent that is an adaptive agent, not a policy. We're not expecting to train a policy here in simulation and just deploy it. We're hoping that an adaptive agent, something that is an agent that's able to quickly learn to deal with new situations, can just as well be deployed in the real world and there quickly learn to deal with new situations.
If there's a tie between domain randomization and pre-training, why not just do pre-training? Because it just gets there quicker with less data.
Not sure it gets there.
It's a little bit quicker, but if you're not seeing a sizable advantage, then there's just like a overhead of setting up the thing for every new task.
But it's very little overhead, right? So the train from scratch after 4,000 rendered examples, which is almost instantaneous, has already caught up. And there could be considerations that maybe worrying that you might overfit to something in ImageNet, and maybe with your rendering you capture better what the invariants are. In practice, though, I think when you look at the result here, it's interesting that you can get away without pre-training, which nobody had shown before. Everything else had done pre-training. And then it's hard to know whether the simulator really, how much a simulator got you compared to what you got from ImageNet. But there is no reason not to pre-train on ImageNet. And one way to think of it is that there's some implicit, maybe, you could potentially argue there's some implicit pre-training on ImageNet because the architecture we use is an architecture, a wiring of the neural net that had been proven successful on ImageNet. And so that wiring we're reusing.
Sure. And
we didn't optimize the wiring in simulation. The wiring was chosen as is. Yeah, there's no reason not to use it, except that maybe you don't benefit much from it in this case. All right, thank you. And here are the papers, but I think I'll send the slides to Abhishek, and then you can just get them online.
MLSH.
Yes.
So the master policy, when it makes